Hello again everyone, welcome back to this lecture tutorial on covalent bonding. In fact, this is actually another separate lecture tutorial series specifically on giant covalent structure, or otherwise known as giant molecular structure. So my personal preference is actually to call it giant molecular structure, but some books and some teachers and some people would have preferred giant covalent structure. Just know that they both meant the same thing. Okay, so the moment you see that term called giant in there, it's not longer single. Okay, so not simple molecular. Simple molecular structure was what we covered in the previous lecture tutorial series. Alright, and these are giant molecular structure. There are a couple of case studies in the what was I going to say? There are a couple of case studies which include describing the giant covalent structure of graphite, diamond, and silicon 4 oxide. Silicon 4 oxide also has another name. It's called silicon dioxide, but the reason why they purposely write down this Roman numeral 4 is because of a concept called oxidation number, and you will learn it later on. This is actually the formal name. So the formal name includes the oxidation number. Includes oxidation number, and oxidation number is something you will learn at a later stage, at a later topic in your O-level or IGCSE chemistry. So the oxidation number there is silicon bracket 4, that refers to the oxidation number of the silicon there. We have to relate the giant structure as well as the covalent bonding of this graphite, diamond to their users, not the silicon 4 oxide, but graphite and diamond to their users. Limited to graphite as a lubricant, graphite as an electrode, and diamond in cutting tools. Specifically is used as drilling bits. Okay, so the very sharp edge, very sharp and very hard edge of drilling bits, especially important for oil and gas, as well as whatever mining industry that require digging into very hard rock surface. And we have to describe the similarity in properties between diamond and silicon 4 oxide related to structure. So this is a comparison between diamond and silicon 4 oxide, but just because they said that in the syllabus does not mean that they cannot ask you graphite and silicon 4 oxide. But there's a reason why they specifically ask you between diamond and silicon 4 oxide, because they want you to think about in terms of their structures, as we will explore in this lecture tutorial. Okay, so without further ado, jumping straight into giant molecular structure. So giant molecular structure contains covalently bonded atoms. All right, so that's the first important thing you have to know. They contains covalently bonded atoms. So you have atoms that are covalently bonded with each other, but they are not simple molecules, because as part of the giant network, you are actually more complicated than just simple molecules. All right, so we have strong covalent bonds, so we need to break many is very important, many of these strong covalent bond, and that is why breaking all these strong covalent bonds between the different atoms in a giant molecular solid give rise to very high melting and very high melting point. So very high melting and also boiling points. So we don't talk about individual separate molecules within the crystals, because the entire crystal is the giant molecule itself. Macro refer to big. Sometimes you will see this term macromolecular structure, but if I were you, I'll suggest you to just stick with one. Giant molecular structure is the same as giant covalent structure, but I personally prefer to use the term giant molecular structure, but there's nothing wrong with the other terms as well. All right, so graphite, diamond, silicon 4 oxide, they're all in your syllabus. So graphite and diamond is what you call allotrope. So what is the definition of allotrope? So allotrope is defined as the different form of an element. So there are different forms of the same element. So we know that graphite and diamond are actually different forms of carbon. So i.e. graphite diamond. So both diamond and graphite are also known as carbon. They are both elements because they only contains one type of atom, which is carbon atom. This diamond also contains one type of atom, which is carbon atoms. So that's why the lattice particle is carbon atoms. What is shown here is a simple representation of the carbon atom being bonded to 1, 2, 3 other carbon atom. So each of the carbon atom in graphite is bonded to 1, 2, 3. Here is 1, 2, 3. Here is 1, 2, 3. So the coordination number of each carbon in graphite is 3 because each carbon atom in graphite is bonded to 3 other carbon. Carbon atom has 4 outer shell electrons. So this is what I said just now. So because within each layer you have covalent bonds to 3 other carbon atoms, I would not be worried about this term called pi bonding because there's A-level stuff, but you can imagine that you actually have between the layers. So what is so unique about graphite structure is that it's layered. So you have this horizontal layer, you have another horizontal layer, you have another horizontal layer. So between the layers you have this thing called weak van der Waals forces. Okay, so van der Waals is just a specific name of weak intermolecular forces. Okay, so you have van der Waals forces of attraction, which is basically weak intermolecular forces between the layers, but between the carbon atoms you have strong covalent bonds. So there are 2 different type of bonding present because this is interatomic bond, this is interatomic, this is between the atoms, okay, whereas the other one is between the molecules, in fact between each layer here. These are the intermolecular forces with van der Waals. Alright, so going back to how the structure was like, so within the structure of graphite, each carbon is bonded to 3 other carbon only. So each carbon only uses 3 out of 4 valence electrons for forming covalent bonds. So what happened to the other electron then? So 1 free electron per carbon atom. So throughout the whole layer structure, you have 1 free electron per carbon atom. So each of these carbon atom has 1 free electron, that has 1 free electron, 1 free electrons. So guess what? Free electrons, therefore, can conduct electricity. Along the layer, which is why your electrical current can be conducted very well along the layer, horizontal layer. But between the layers, where you have the weak van der Waals forces holding the different layers together, you have poor electrical conductivity because your electron cannot move in this direction. Your electrons can only move along the layers because you have 1 free electron per carbon atom, which can move freely, we can move freely. Okay, so the idea is it can get delocalized along the horizontal layer. You get good conduction along the horizontal layer, but not between the layer. So as I mentioned just now, so graphite has very high melting and boiling point because you need to break many strong covalent bonds between the carbon atoms. So do change your notes a little bit. So within the layer might not be that clear without emphasizing that you have to break the many strong covalent bonds, but there is a result of graphite having giant molecular structure. So question will always say in terms of structure and bonding. So you will first start off by saying graphite has a giant molecular structure. Therefore, you need a large amount of energy to break the many strong covalent bonds between the carbon atoms. Alright, so therefore it has high melting and boiling point. Volatile, so simple molecular structure usually means you have volatile molecules because they boil easily. these things are very high value. They are not volatile at all, okay? So you're not expected to actually remember any of these values, but you got to appreciate that these are very high. When you talk about graphite, very, very, very high melting and boiling points, okay? In addition to what I said just now about electrical conductivity, so you gotta be able to explain in terms of graphite. In graphite, you only has 3 out of 4 valence electrons on the carbon are used in bonding. So 1 free electron per carbon atom means that it can delocalize freely. Delocalize means move freely. Of course, only along the layers. I don't care about this term pi. You don't really need it for your O-level or IGCSE concept. Alright, so they only conduct electricity in the plane of the layer, but not at right angle that is between the layers, because, well, the electrons can only flow along the layers but not between the layers. Okay, you don't really do property 3 in IGCSE or O-level syllabus because you don't really talk too much on the solvent stuff, but number 4 is important. We talk about the weak van der Waals forces between the layers. It means just like the covalent bonds, which require a large amount of energy to break, but the weak intermolecular forces between the layers, they are considered quite weak compared to breaking covalent bonds. Therefore, you can slide over the layer easily. And therefore, if you can slide over the layer easily, graphite is very slippery, as well as it's being used for lubricating properties. Okay, so if you take a graphite pencil and you start sketching some stuff on the drawing paper, you start making things like things like this, and then you put your hand on it. You put the palm of your hand and rub it on this thing which was drawn with pencil, and you realize that you have that slippery sensation, and that is actually a result of the van der Waals forces. They are easily overcome, they are easily broken between the layers, that makes the graphite itself very slippery and therefore useful for its lubricating properties. All right. The second case study, which is another allotrope, another form of this carbon as an element, also has carbon atoms as the lattice particles, and you also have the strong covalent bonds between the carbon-carbon atoms. But something is different here, because each carbon is bonded to 4 other carbon. Each carbon is bonded to 4 other carbon. It's a giant covalent network, is a giant molecular structure. Therefore, it actually continue on and on and on. Okay, so it's not a layered structure like graphite. It's actually all the carbon atoms are used for forming 4 single covalent bond. All right, so here the coordination number is 4 because each carbon is bonded to 4 other carbon. The coordination number of carbon in graphite was 3 because each carbon was only bonded to 3 other carbon. So in terms of properties, we also have giant molecular structures. Diamond has a giant molecular structure. Therefore, you require a large amount of energy to break the many strong covalent bonds between carbon atoms. So I just want to specify it's between those atoms. Again, this value is not really that important because no one is expected to remember actual values, but just like graphite, they are close to 4,000 degrees Celsius, very high melting point. We don't even talk about the boiling point at all. All right. And then in terms of conducting electricity as well as conducting heat, because each of the carbon in graphite, in diamond, has formed 4 covalent bonds to 4 other carbons. That means there are no mobile or no free electrons in order to conduct, because all the 4 valence electrons of carbon have been used for forming 4 covalent bonds. All right, so you don't necessarily have to actually word by word come up with stuff that from your notes, but you really have to relate that how many covalent bond has each carbon formed, does it have any free electron left, or does it not have any, such as this case here. When the carbon form 4 covalent bonds, the carbon will have no more valence electron left, and therefore it cannot conduct electricity because no free electrons, no more free valence electron Of course, it still have inner shell electrons, but we talk about valence electrons when we talk about chemical reactivity, chemical properties, physical properties, all down to the valence electrons itself. All right. Just like for graphite, we don't talk about the solubility in solvent, but we do talk about very hard. So just now, graphite was slippery. Graphite is slippery because of the breaking weak intermolecular forces, the van der Waals forces between the layers, and therefore you use it for lubricating properties. On the other hand, diamond is very hard. It's not slippery. It's not lubricating property at all. So in fact, it's very strong and very rigid. Okay. So what happened then is it's actually very hard. It's one of the hardest natural substance known, and therefore we use in drilling bits. Okay. So drilling bits are important for mining, for petroleum industry, oil and gas industry, which our country definitely depends on. So a lot of those things, when you drill into the ground, you will have something like this, and then that tip there will be made of diamond. Because it's very hard, you just keep on piercing into the ground, into the very hard rock underground. All right. The third and the final case study of your giant molecular structure, compound with giant molecular structure, is this thing called silicon 4 oxide, is SiO2. So this is no longer an element. So this is not an element. It is not an allotrope of any element. It is a compound. It is a compound because it consists of two or more elements. In fact, here is two elements. They are chemically bonded in a fixed ratio. One silicon, two oxygen. Have a look at this one silicon, two oxygen. Therefore, the formula is SiO2. So this diagram looks complicated, but I just like to highlight it by redrawing it, okay, and emphasizing silicon. Silicon is in group 4. It is just below carbon. It has 4 outer shell electrons, 4 valence electrons. It can form up to 4 covalent bonds typically. All right. So just like carbon, it forms 4 single covalent bonds because it's bonded to oxygen. Okay, the Si is bonded to 4 oxygen. Each silicon is attached to 4 oxygen atoms. That is your first point. The oxygen is in group 6. Remember your group 6 chemistry, when oxygen form covalent bonds, it can form up to 2 covalent bonds. This oxygen has already formed 1. This means a single covalent bond. So oxygen formed 2 covalent bonds, therefore there is another bond here. There is another bond here. There is another bond here. There is another bond there. Alright? So now, what is this oxygen bonded to? It's bonded to silicon here. It is again bonded to another silicon, another silicon, another silicon, and another silicon. So each oxygen atom is attached to 2 silicon atoms. So this is a really important concept when you have to sketch it out. And I know it's a giant molecular structure, so it just continue on and on and on. Remember, each silicon is bonded to 4 oxygen. So blah, 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 blah. Each silicon bonded to 4 oxygen. 1, 2, 3, 4. The silicon is in group 4. It forms 4 single covalent bonds. Each oxygen is bonded to 2 silicon. So oxygen is in group 6. It forms 2 covalent bonds to reach the noble gas, or to achieve the noble gas configuration of neon, which is the closest to it, right? Sorry, that was just my alarm going off for a chore that I had to do at home. Anyway, so getting towards the end now. So what else did I miss? So again, we need to think about the properties. So it has a giant molecular structure like that of diamond. So if you think about diamond, each of the carbon is actually bonded to 4 other carbon, but on the other carbon is also bonded to 4 other carbon, unlike here where the oxygen is actually bonded to 2 silicon instead of 4 silicon. So there's the difference, but in terms of similarities in properties, this one also has a giant molecular structure. So you start off your essay like that. I say it's an essay because, well, it's typically something that you can prepare for. You got to talk about the structure, and then we need a large amount of energy. You got to emphasize on the large amount of energy, or huge amount of energy is required to break the many strong covalent bond. But we need to be specific in the context of SiO2, so this is between Si and oxygen atoms, simply because this is SiO2. But why do I require a large amount of energy to break it? Because I am doing melting, or if you're really serious, you can think about boiling, but you gotta melt the solid first, and the solid will have a very high melting point, just like diamond and graphite, because of the structure as well. And you need to break the many strong covalent bonds within the giant molecular network there. Okay, so that's it on SiO2 and on the diamond as well as graphite. Those three are the major case study for giant molecular structures. In fact, the same is true for most 14 to 16 years old chemistry curriculum all around the world, whether you're doing the O-level, the IGCSE, or whatever other curriculum that you call it, which are not the British curriculum. Okay, so I'll leave it here for this lecture tutorial. In the next lecture tutorial, I'll continue on metallic bonding, which is the last bit of chemical bonding of this topic. Okay, so see you in the next video. Thank you for watching. Follow me at ptet.chemistry on IG, Facebook, and Twitter if you use these social media. Otherwise, you can just subscribe to the channel. Click the button on the bottom right to subscribe to the channel and get all future updates at your fingertips. Okay, see you in the next video. Thank you for watching.